It's literally what it says. Ray traced audio. And it's impressive. Fucking new tech.
Confused by audio in games, where you couldn't tell which direction a sound came from? I've spent 7 years creating a game engine, and I figured out a way to use ray tracing to get realistic 3D audio. And it can also be used to visualize sound for deaf people. This process has 3 steps, and the first is about tricking your brain. Your brain relies on many factors like the shape of your ears to work out which direction a sound came from. But in games, you can only hear sound from your left and right headphones. To solve this, games use binaural audio, which simulates how sound waves interact with your head and ears. This tricks your brain into thinking a sound came from a specific direction.
And the thing is that binaural audio is pretty much, you have 3 floors. So you're standing right here. If you look up, if the audio is lowered, that means that the player is underneath. But if you look downwards and the sound is louder, that means that the player is underneath you.
Most games use this already, but they still have issues with their audio. We can solve these problems using ray tracing. Let's say you're working in an office and someone's talking in the room next to you. When you hear them talk, their voice will be deeper than usual. But you don't think, that's strange, Jamie's voice sounds really deep today. Your brain subconsciously understands that there's something between you and them, and that their voice will sound a bit deeper than usual. Then if their voice sounds normal, you'll know that they've opened the door. Just by listening, you've noticed things about the environment around you, and this is crucial for 3D games. To muffle sounds, most games use a room-based audio system. So if you're standing in this room, sounds in the other rooms will be muffled. But it gets complicated when rooms have strange shapes.
And not just that, when you introduce the verticality also.
If you're standing here, how muffled should a sound over here be? And it gets more complicated because some rooms might have thicker walls, doors that open and close, or they might even be destructible. This is where ray tracing comes in. Instead of setting up rooms for our level, we'll fire rays outwards from your player. These rays travel faster than your eyes can see, so I've slowed them down for this demonstration.
And the thing is, you don't have to do anything, right? You don't have to do any fucking setup. You put RTX audio in your game and it just fucking works. That's what is impressive, right?
Also move in 3 dimensions, but these animations use 2, so they're easier to look at.
And you cannot make it more consistent than that. You can't. The thing is, the range of the different audios that we will have one day when this becomes norm and standard, right? The amount of the different audio cues that you're gonna be getting, you're gonna need so much game knowledge. It's crazy.
Also, in real life, sound travels towards your ears, but these rays are doing the opposite. This isn't a perfect simulation of real life. These rays are trying to discover sounds and learn about the environment around you. We don't have any sounds right now, so I'll play some music in this room. Now we can see a new kind of ray that travels directly towards the music. The more green.
By the way, this is what he's doing from the player bouncing towards the sender. The same way the graphics look like. It is calculating wall bounce to the light source, and that's how RTX is being calculated. Literally the same.
Rays there are, the clearer the sound. Listen to how the music changes when the room closes up. We can change the entire shape of this building and the rays will automatically figure out how muffled the music should be. But ray tracing can do so much more than this. Here we're inside a large room and we'll fire rays outwards like before. Each time the rays bounce, they'll check for line of sight back to your player. These blue rays represent echo in real life. I used to think echo was just based on the size of the room, but one day I helped my parents empty out their garage. As we cleared out more stuff, the echo got stronger. That's because there were no more cars and other stuff lying around the garage that sound could get lost behind.
Now, developers need to manually not just put rooms with the boxes, but they also have to add reverbs, echoes, and all of that shit. Everything manually. With this, automatic. It just works.
Now that it's empty, nearly all the sound is reflecting off the walls and back to my ears. The room is the same size as before, but the echo is much stronger. To have accurate echo in every scenario, we need to blend between a few states. The first state is a small room where you hear the echo instantly. This could be a bathroom where the walls are very close to you. The second state is a large room where the walls are far away. It takes a while for these blue echo rays to return to you, so the echo sounds delayed. We'll blend between these two states based on the length of the blue rays. The next step is related to the garage from before. If all of the blue rays return to you, then the echo should be loud. But as less blue rays return to you, the echo should be quieter. This works great, but it only applies to indoor sounds. We need to support outdoor environments as well. If our building has some broken walls, some of the rays will leave the building. If they reach the edge of the level, we'll say that they escaped outdoors. As an optimization, these rays will keep bouncing around so they can gather more data. Now we can blend between an indoor and an outdoor state based on how many rays escape. Now that we can tell if a player is inside or outside, we can add another cool feature. When you're at home in a thunderstorm, you'll hear muffled rain all around you. But if you open a window, it'll sound like the rain is coming from that window specifically. We can simulate this using the escaping rays. The average direction of all escaping rays is the direction we should hear the rain from. But what if we're in another room and we don't have clear line of sight with the window? Let's follow the path of one ray. Since it eventually escapes out the window, we can use it to figure out the direction of the rain. We can do this using the blue echo rays. The last blue ray is the direction that we should hear the rain from. I'll colour this ray yellow and repeat the process with every ray. The average of all these rays is the direction we should hear the rain from. As your player moves around, you can see the rays point towards the window. The final feature is related to wall thickness. Here we have two rooms and the one on the left has thicker walls than the right. Sounds in the thin room should be less muffled than the thick one, but currently our rays stop when they hit a wall. So let's use a new kind of ray that travels all the way to the sound. The longer these rays spend inside a wall, the more energy they'll lose. Let's graph this energy on the right. Each column represents one ray and its height is how much energy it has. When the speaker moves inside the thicker room, we can see the energy drop. To work out how muffled a sound should be, we'll use the green rays from before as well as the energy left in these orange rays. When used together, these four ray tracing features produce realistic audio in complex environments. But we can also use ray tracing to visualize sound for deaf people.
Won't this be laggy as fuck? Just watch.
Somewhere here there's an enemy firing their
I was also skeptical.
gun. Since deaf players can't hear them, we need another way.
I was also skeptical just because it's RTX, right?
Somewhere here there's an enemy firing their gun. Since deaf players can't hear them, we need another way to locate them. Before we were casting rays outwards from your player, but instead we'll cast rays outwards from the enemy. When these rays hit a surface, a small dot will appear there. As the enemy moves around, the dots will update in real time. If the enemy stops making noise, the dots will disappear. Some sounds like explosions can be heard from far away, so the dots should be larger. But when an enemy is sneaking around, the dots should be smaller. The colour of the dots can also convey the type of sound. Gunfire could have red dots and footsteps might have green dots. If a player is colourblind, we can also change the shape of the dots. Deaf players can now see 3D sound visualised around them. I'm still working on this feature and I'd love to hear your feedback.
This is gimmicky, but you can literally play the game with the music blasting, homie. You know? It is gimmicky, but it is really useful for deaf people, dude.
Do you need an expensive graphics card to run this? The answer is no. This system works on everything from old laptops to the latest spaceships. That's because when you play a game, your input is handled by your CPU, which tells your graphics card what to render, and then your monitor displays it. Whereas ray traced audio runs on background threads on your CPU, and then sends the output to your headphones. This separation allows your game to continue to run smoothly. The ray tracing is also performed against a voxel grid, which is...
I mean, the thing is, in a lot of games, CPU is the thing that is bottlenecking, right? So, you know, I guess it is gonna vary, but there is nothing. What GPU has to do with the audio, dude? You know? This is such a cool feature that homie, even if it is expensive, like building the whole fucking game around the audio, dude, would definitely be worth it, dude. For this kind, like...
The ray tracing
the quality that you're getting is just ridiculous. Ridiculous.
The ray tracing is also performed against a voxel grid, which is much faster to ray trace against than triangulated models.
It's ray traced, which means that you can always like there is gonna be a slider to increase the amount of the bounces and decrease the amount of the bounces, right? Like in real world, this
State is a small room where you hear the
this bounce happens indefinitely until thing loses its energy, right? And then it dies out. In the video games, even when you're doing ray tracing, you're having a slider to increase or decrease the amount of the bounces, right? Without of any RTX, without of anything, it is one bounce, which means that when it hits the glass, it stops, for example, right? So yeah, I don't see the performance being issue in that at all.
which is much faster to ray trace against than triangulated models. The size of the voxels can also be increased to make it run even faster. This ray traced audio system will be available as a paid plugin for major game engines soon, but I need
You ain't got
your help testing it. If you're a game developer, let me know if you'd like to help out. The code for the rest
I like how he excluded Unity.
of my engine and the animations in this video
I love it.
can be accessed in the video description. I
What
also
a
optimized
fucking
another
chud.
kind of ray tracing up to 11,000 frames per second, which you can watch
What
in
a
this video on screen.
fucking Chad. Wait, hold. Wait, can I buy it? And
But
homie, if it costs $800, people are gonna fucking buy it. Let's be real.